So in part 2 of the periodic properties, I'm going to cover three other important properties. One is ionization energy, electron affinity, and electronegativity. So I will be discussing how these three periodic properties vary along the period as well as along the group. Also, I will discuss the factors affecting ionization energy. So, like as you know, these there are many important factors which affect the ionization energy. Ionization energy, as you know, you have to supply some extra energy to pull the electron, that is the valence electron from an atom, and you have to move the electron from that valence shell to the vacuum. So that energy is called as ionization energy. Basically, you are polarizing that molecule, so removing, supplying energy and removing the electron from the valence cell. Okay. So that the net nuclear charge toward the valence shell electron will be changing. As a result, effective nuclear charge will be altered, and the atomic radii or ionic radii will also be altered. As a result, these are the important factors which will influence the ionization energy. First one, will discuss about the atomic size or radii. If you look at the size, the larger the atomic size, smaller will be the ionization energy. What is the reason? The larger the atomic size, the valence electron will be away from the nucleus. As a result, more shielding effect if it is smaller size. But if the atomic size is larger, the shielding effect will be less, shielding constant will be less, and the net pull experienced by the valence electron will be less. So, since the less energy or the pull experienced by the valence electron, you can supply minimum energy, or the ionization energy will be smaller. It will be vice versa. If it is a smaller atomic size, then it will be tightly, the valence electron will be tightly bound with the nucleus, which means the sealing constant will be more, the nuclear charge will be more, and you can't remove that valence electron easily. So you have to supply the more energy. So remember, larger the atomic size, smaller will be ionization energy, and vice versa. And magnitude of nuclear charge, net nuclear attraction towards valence shell electron, that is what we call as nuclear charge. The magnitude is very, very important. If the greater the effective nuclear charge, more tightly the electrons will be with the nucleus. Hence, more ionization energy you have to supply. So that we already discussed. So now let's take some examples like atoms like lithium, beryllium, boron, carbon, nitrogen, and fluorine, and neon in a particular period. So how about their nuclear charge? When you move from lithium to neon, the nuclear charge increases, one count it is increasing like +3 to +4, 5, and up to +10. So the ionization energy, look at here, when you move along this period, I already told, when the nuclear charge is increasing, the ionization energy we supply will also increase from 520 to 2801. So it increases. But there is some anomaly which has been rounded circle for clarity. Empty and half filled and completely filled electronic configuration have extra stability. For instance, the ionization energy of beryllium, which is filled to 2s electron, because it is completely filled, the 2s orbital, and nitrogen have half filled and they are more stable. As a result, they have higher energy. For example, 1080, for instance, if you move from lithium to beryllium, actually beryllium should have 800 and 900, but it's other way. The reason is it is more stable 2s orbital, because two electrons are filled in the 2s orbital, so the energy is higher. Here nitrogen half filled, so the energy required, ionization energy is other way, not 1314, it is having 1403, then 1314. This is the reason. So this anomaly you should understand. The ionization energy of boron is less than that of beryllium. This already we have discussed. So the s electrons screen the nuclear charge more effectively than p electron. Okay, how they vary across the period. Moving from left to right? The ionization energy increases in the increase in atomic number. You can't, it is very difficult to remove an electron from a system with an octet configuration, which is why the ionization energy value is very high for the neon, that is the inert gas with octet configuration, noble gases. Variation down the group. In a group, the ionization energy decreases from top to bottom. The reason is atomic radii or ionic radii is also increases along the group. As a result, the distance from the nucleus, the valence electron distance from the nucleus will be increasing. As a result, the two important criteria, the effective nuclear charge, net nuclear charge will be decreasing. Here, when you move across the period, it is increasing. When you move across the group, it will be decreasing effective nuclear charge. That is the main reason. So this point you have to remember. So these are the major factors that influence the ionization energy and the trend of the ionization. Now, there is another factor called penetration effect of the electron. So the penetration power is more for S than P. So the ionization energy increases as penetration effect of electron increases. So the penetration effect is more for S than P, D and F. As a result, the ionization energy is more for S, then followed by P and then followed by D and F. So S orbital electrons has more ionization energy than P orbital electron due to more attraction towards nucleus. The first ionization energy. So there are different types of ionization energy. When you are removing one electron, that is called first ionization energy. Then again, if you are removing one more electron, that is called second and third and so on. The first ionization energy of magnesium is greater than that of aluminum. So the reason is the penetration power of S orbital is more than P orbital. Okay, the other factor is screening or shielding effect of the inner shell electron. We know that shielding effect is caused by the inner electrons on the attraction of the outermost electron by the nucleus. The larger the number of inner electrons, greater will be the screening effect. That is the screening effect on the outermost valence electron. Thus, one can say that valence electron experiences less attraction. As a result, the lower will be the ionization energy. So the more the number of inner shell electron, shielding effect will be more, and then less ionization energy is required. Moving down in a group, number of inner shell increases. As a result, ionization energy decreases. That we already discussed. Stable electronic configuration, remember, like half fill or like nitrogen or fully fill, like we have seen that beryllium boron comparison. We have seen that beryllium has a 2s completely filled one, so it is more, it is having extra stability, ionization energy will be higher. So remember that point. So in your examination, they will ask define ionization energy. What is the trend of ionization energy across the group and period, and what are the factors influencing ionization energy? Mostly 8 mark question they will ask. And some numerics can also be asked, like ionization energy of one hydrogen atom is 2.18 into 10 to the power minus 18 joule. Calculate the ionization energy of hydrogen atom in kilojoule per mole. And there are also other numerics like ionization potentials will be given, and you have to predict the ionization potential of the following atom: lithium, sodium, potassium. So sodium is in between lithium and potassium. You have to calculate the trend, that is the ionization potential. And ionization of energy of magnesium to magnesium cation, that is 3.2. The first ionization energy they have given. Second ionization energy you have to calculate for magnesium, like that. First ionization energy given, second you have to. So these are some of the numerics. The other type would be you have to calculate the effective nuclear charge Z star for valence electron, 3d electron, 3p. This you have to apply this latest thing that also we have discussed already in the part one. Now, electron affinity. So this is something energy released. Electron affinity means you are adding an extra electron to the valence cell. So when you are adding an extra electron, you have to supply some energy. Whereas when you are taking an electron out, electron energy will be released. Here, an energy is required. So the amount of energy released when an extra electron is taken by neutral gaseous atom to form a monovalent gaseous anion. So here you are adding an electron and then you are forming an anion and energy will be released. Mostly the amount that is the electron affinity, unit of electron affinity is mentioned or denoted in electron volt or kilojoule per mole. Successive electron affinities, which means EA1, EA2, etc. When an electron has to be added to a gaseous atom, the energy is released, which means it is negative, and it becomes a negative ion, that is anion. However, if you add a second electron to an anion, then already one more negative charge is there, and it will be opposed by the electrostatic repulsion, electron-electron repulsion. Hence, the energy required to be or supplied for the addition of second electron will be higher. Second and successive electron affinities are positive. First one will be negative, second and the successive ones are positive. For example, first electron affinity value EA1 for oxygen to oxygen anion is minus 141, whereas second electron affinity value is positive. The reason we already discussed. Okay, factors influencing electron affinity. Now we will ask what is electron affinity, how, what is the trend. So now we have in the previous slide we have discussed about electron affinity 1 and 2, right? Now size of the atom, atomic size, effective energy, same thing like the ionization energy. Whenever the size of the atom is smaller, higher the value of electron affinity. That's why in the period it increases. And effective nuclear charge, same. Higher nuclear charge, higher electron affinity. Okay, variation along the period. So moving from left to right in the period, the size of the atom decreases uh, and their nuclear charge increases. Moving from left to right in a period, the size of the atom decreases and their nuclear charge increases, and hence electron affinity value will be increasing. Now, let's take the group 7A halogen series, which have the highest electron affinity value. The reason is their tendency to acquire an additional electron to form the stable octet. Like the 7 electrons will be in the outermost shell, and when they add one, 8 octet it will be. That is the reason. On moving down a group, size of the atoms increases significantly, which leads to decrease in the electron affinity. When you move from fluorine to iodine, size increases, so the electron affinity value decreases. Look at here, minus 328 to minus 295, so the value is decreasing. Variation of electron affinity in the periodic table. So now we will see the electron affinity variation in the periodic table. You have fluorine, chlorine, bromine, and fluorine as well. So it should be iodine actually. There is a typo. So when you move from fluorine to chlorine, there is an increase, and whereas here it is decreasing. The reason is we already discussed about the offset one, and also the reason for lower electron affinity values for nitrogen, oxygen, and fluorine is suppose if you have the inner electrons and your nucleus is there, there will be higher electronic repulsion when there is the incoming electron you are adding, smaller atom case. But in the case of fluorine, the atomic size is large. As a result, when the incoming electron will experience less or lower electronic repulsion, that's why it is low. Okay, for example, fluorine, it is high because it is a smaller atomic size or atomic radii. So the nucleus will, the higher electronic repulsion will be there. Incoming electron will experience the higher electronic repulsion, but it is the other way for the larger atom, that is the iodine or bromine. So this reason I have explained, smaller size of this atom in each group creates an increased electron repulsion. That is the reason for higher electron repulsion. Now let's move on to the third important the periodic property, which is electronegativity. Like as you know that chemical property describes the tendency of an atom in a molecule to attract the shared electron pair towards itself. If you have a bond, one of the atom will be having a tendency to attract the bonding electron pair towards itself, which means it is having higher electron negativity or tendency to pull the electron towards itself. So obviously it will gain some partially negative charge, and that's why here you are putting when the electron in the middle is moved toward the atom B, it gains the negative charge, partial negative charge. So this is actually moving away from A, so it is gaining del positive. Electronegativity is referred to electron attracting power. Okay, smaller the atom radius, it will have a larger electron. Okay, now let's take the example fluorine to iodine. Which one is having the smaller atomic radius? Fluorine. So obviously, if you are having a HF bond, fluorine is more electronegative than hydrogen due to the smaller atomic radius. As a result, the electron pair will be moved towards fluorine. So imagine A is hydrogen, B is fluorine. Fluorine is having smaller size, so the electron will be moved towards fluorine. As a result, fluorine will gain del minus and hydrogen will gain del positive. So this type of bond is called polar bond. Initially it was covalent bond, but due to the electronegativity difference between hydrogen and fluorine, or A and B, the bond becomes polar bond. If B is more electronegative than A, then this electron pair will be completely pulled towards B and it gains negative charge, whereas A will gain positive charge. This type of bond, and now you understand how um, you know the bond in a molecule like HF is converted or behaves from covalent nature to ionic nature, that is entirely due to the electronegativity difference. So the variation of electronegativity in the periodic table along the period, that is from left to right, the electronegativity will be increasing. That's why compared to lithium, the fluorine, if you move along that series, it will be having higher electronegativity. Any period, if you move across the period, electronegativity will be increasing left to right. The reason is the size decreases and nuclear charge increases. So inert gases have zero electronegativity. Why? Because they are more stable and they have the octet configuration. Electronegativity decreases from top to bottom due to increase in atomic size. We know that atomic size increases across or along the group. As a result, electronegativity decreases. So higher oxidation state have more electronegativity due to greater attraction of electron. For example, compared to 2 plus stannous, stannic, that is SN4 plus will be having higher electronegativity 1.94. Hybridization dependency, for example, compared to sp3, sp will be having higher electronegativity and then sp2 and sp3. Formal positive charge can also increase the electronegativity, whereas formal negative charge decreases. Formal positive charge increases electronegativity, whereas formal negative charge decreases electronegativity. You look at here, formal positive charge, it will increase. So this is having higher electronegativity than the formal negative charge in H2 and F. So the greater the electronegativity differences between the bonding elements, greater the ionic character of the bond. For example, hydride, HF, HCl, HBr, HI. So HF will be, if the greater the electronegativity differences, look at here from HF to HI, HF 1.9, HCl 0.9, 0.7, 0.4. As a result, since the electronegativity differences decreases, the ionic character of the bond will increase. The ionic character, see the value 46 to 5, it is decreasing. There is also another one called Millikan scale, which you can calculate the electronegativity by calculating the sum of ionization energy and electronegativity, electron affinity, and over 2. So you are averaging that and dividing by 2, that will give you the electronegativity value. What does it mean? If you know the ionization energy value of for an atom, for example, say fluorine, and if you know the electron affinity value for the fluorine atom, it's just sum of that and divide that with 2, you will get the electronegativity value. That is called Mulliken, or Mulliken, it is called as Mulliken scale. S character. So it depends upon the covalent bond. For example, you have to calculate the S character, percentage S character, and the electronegativity value trends, or can also vary. For instance, hybridization. Let's take the example like acetylene, ethylene, and ethene, like triple bond, double bond, diene, and then the aliphatic or simple aliphatic compound with the sp3 hybridization. So the hybridization will be sp for alkyne and sp2 for alkene and alkane sp3. Since here the sp character, percentage s character, here it will be 50-50. Here sp character will be 33, and then here 25 percentage yes and 75 percentage p character. Okay, here it is 33 percentage. P character will be the other way, 50-50 in the case of sp, and since it is 33, the remaining will be p character. Similarly, since 25, 75% will be p character. And then electronegativity value based on the sp, if it is sp character is 50-50, electronegativity will be more, and when it is sp2, the s character will be less than 33 compared to 50. So obviously 2.75 is even lesser, so the n value will be lesser. So this is how the trend between the percentage s character and n value. As a result, electronegativity value of alkane is lesser compared to alkene. The reason is S character is more for the alkene compared to the alkane. It is ethane. Okay, so this is the final slide. In this one, I would like to present an overall view of the periodic properties, all 6 properties, like atomic radius increases along the group. So when you move from top to bottom, this group. When you move from left to right, this period. So atomic radius increases along the group, and when you move across the period, especially from top right to left also, it increases. But when you move from left to right, it decreases. That we already discussed. Ionization energy, it increases in the period as well as in the group, and electron affinity increases along the period as well as group. Metallic character increases from noble metal to, for example, S block element. It will increase. Non-metal character, when you move from alkali and alkaline earth metal to noble gases, non-metallic character will increase. So this trend you have to remember. When you remember this picture, then they will ask any one periodic property. They will ask you to define that periodic property, and they will ask you to explain the trend in group and period, and they will ask you to explain the factors influencing that particular property. So they will ask 8 mark question, and the mark distribution will vary. 2 mark for definition, and trends may be 3 mark and 3 mark for the factors. It may vary. Even 4 mark they can allow to the factors, and they can split it to each for definition and the trend. Okay, so I think with this one part 2, I have completed the remaining 3 periodic properties. So read those 6 periodic properties and understand their trend, and understand what are the important factors or key factors that influence that particular periodic